Hello everyone and welcome to the 8th lecture of the second edition of the Current Topics of Heritage Science series of E-RIHS Academy. This series is organized by emerging professionals in the frame of the E-RIHS project and European research infrastructure of heritage science. My name is Diego Quintero Balbás. I am a researcher of the National Institute of Optics in Florence, and I will be moderating today's lecture. Our topic today is electrochemical techniques for studying metal corrosion on heritage objects. The recording of this lecture will be available later on the E-RIHS YouTube channel. At the end of the lecture, you will receive a survey. Please take a few seconds to let us know your opinion. You can ask questions through the Q&A function at the bottom bar of the Zoom window, and if you're experiencing any technical difficulties, you can contact us using the chat. So today it's my pleasure to introduce our speaker, Dr. Emilio Cano. He is a senior scientist at the National Center of Metallurgical Research, CENIM, of the Spanish National Research Council, where he leads the research group Atmospheric Corrosion and Conservation of Cultural Heritage, CAPAC, focusing on the study of corrosion and protection of metallic cultural heritage, atmospheric corrosion, and electrochemical techniques. He has participated in over 40 research national and European projects, having published more than 100 articles in index journals and over 120 contributions to conferences on these topics. He is fellow of the International Institute of Conservation, and he served as an assistant coordinator of the Metals Working Group of ICOM-CC from 2012 to 2020. He coordinates the TechnoHeritage Network for Science and Technology for the Conservation of Cultural Heritage from 2015 and 2022. And currently, he is the co-coordinator of the CSIC Interdisciplinary Thematic Platform, Open Heritage, Research and Society, and the national coordinator of the Spanish node of the European Research Infrastructure for Heritage Science, E-RIHS. Dr. Cano, thank you for being here, and the floor is yours.
Okay, thank you, Diego, thank you, Antonina, and thank you all the organizers of this series of current topics of EIHS Academy. It's my great pleasure to be here today explaining very quickly what I do and what is my research in my work about. I will start sharing my screen now. I hope you can see it well. Okay, so as it has been announced, I will be talking about electrochemical techniques for studying metal corrosion on heritage objects. These techniques are not so popular as other techniques used in heritage science. So the first question is why using this technique? And the answer is this: it's corrosion. Corrosion is the reaction of metals with their environment, and it is something that happens to almost all metals in all kind of environments. Specifically for heritage metals, they corrode during burial. For archaeological objects, they corrode when they are exposed to the atmospheric environment, and they corrode even in museums by reaction with the pollutants and the humidity of the museum. Type of corrosion we find in cultural heritage is mainly the so-called electrochemical corrosion or wet corrosion. It is named this way because it's produced by reactions that take place within an electrolyte. For instance, in atmospheric environment, it is the unabsorbed layer of water or of wetness, and within that layer of electrolyte, we have two types of reactions. First, in some areas of the metals that behave as anodes, we have the oxidation, the dissolution of the metals, forming metal cations and producing electrons. These electrons are used in the cathodic areas of the metal to produce the so-called cathodic reaction, in which some species, typically the oxygen and in the environment, are reduced to form different ions. These anions and cations react within the electrolyte and precipitate and form the corrosion layers. And as you can see here, we have ions and we have electrons moving around. That is, we have electrical current. So you can easily understand that if we are able to measure or to control this movement of electrical charges, we will be able to measure or control the corrosion process. And that's the basics of the electrochemical techniques, measuring or controlling the movement of these charges in the anodic and cathodic reaction. Within the field of metal conservation, electrochemical techniques are better known as a tool for conservation treatment, for restoration treatments. They started to be used at the end of the 19th century by Friedrich Röntgen, and they became very popular at the mid of the 20th century. For instance, in this image you see here, it is taken from the Plenderleith book, the Conservation of Works of Art, which dedicates a lot of pages to these techniques. There was a decline in the use of these techniques in the 70s because mainly because of changes in criteria or in the results that were sought in the restoration treatments, but they have had an interest at the beginning, starting the beginning of this century. On the other side, electrochemical techniques are widely used in research laboratories and in industry to study corrosion and for the assessment of protection systems. In most cases, these electrochemical techniques are, let's say, the backbone of the techniques used for corrosion studies. But notwithstanding that, it is true that those techniques are not so widely used for studies of corrosion and protection systems for metallic cultural heritage. This is something that has been changing in the last years and have become more popular. And well, I hope that after this lecture, some of you will learn a bit more about them and start using them or considering them for your studies. When we want to study metallic heritage, of course, we have different techniques or different approaches depending on what we want to study. If we want to focus on the aesthetic or historic values, of course, we can use visual inspection of reading historical sources with any historical study. If we want to learn and to investigate the composition and microstructure of the metals, surface, patinas, we have plenty of analytical techniques. I'm sure most of you are familiar with them: X-ray fluorescence, Raman, SAT-D, microscopy, LIBS, etc. Many of them, or some of them, have already been presented in this lecture series. But if we want to really understand the corrosion process, that it is taking place, what is happening for the corrosion, the answer are the electrochemical techniques. The advantages of these techniques, several. I am mentioning here some of them. The first one is that they have a very high sensibility. For instance, here you see that for mass loss of 10 nanograms of mass loss during a corrosion process, which is a mass that is very difficult to measure, for a corrosion process of oxidation of iron to iron 2, that is, in electrochemical terms, can be measured as a current of 1 nanoampere per square centimeter for 1 hour. This current, which seems very small, is, however, very easily measured with any piece of electrochemical equipment, current electrochemical equipment. Actually, a few orders of magnitude less current can be very easily measured. Thanks to this sensitivity, we can measure instantaneous corrosion rate. So we can measure the corrosion rate at this moment, and then after some exposure of the metals to the environment, or after some time, or doing actually a continuous monitoring of the corrosion rate and see how it is changing. And in some cases, they can be non-destructive, which is very relevant for our field. It is not true for all electrochemical techniques. It is only in certain cases. We can measure in real conditions, and as I say here, even on real objects. So this is also very relevant for our case. We're not only measuring on samples that we take, that we can measure directly on the objects, and we will see a bit later of that. And finally, it is a relatively simple and inexpensive equipment. Starting with this last, with the equipment, the measurements, to perform these electrochemical measurements, we need to build what we call an electrochemical cell. It is a setup in which we have typically 3 electrodes. We can measure also with 2 or even 4 electrodes, but the most typical setup is with 3 electrodes, in which we have the working electrode, which is the piece of metal we are measuring. It can be a coupon, or it can be, in our case, the real artifact, the object, the sculpture we are measuring. Then we have a reference electrode, which is a reference to measure the electrochemical potential, typically an electrode or silver chloride electrode. And we finally have a counter electrode, which is an inert electrode that is used to apply the current into a closed circuit. All this is connected. This is a typical electrochemical cell. We put that within an electrolyte, which put some electrolyte that we can choose depending on what we want to measure. And we connect that to a potentiostat. It is this device. This is one example of a small one that we use for field measurements, and that is controlled by a computer. So you see, it is not something large or expensive. Might have noticed that I am referring to electrochemical techniques in plural, and that is because it is actually a whole family of techniques. It's not a single technique, but all of them are based basically in the same 3 parameters, which are the potential, E, the intensity of the current, which is I, typically mention or use the symbol I, and the time, T, or the frequency. So, and then depending how we manage these parameters, what we apply, how we keep them constant or scan them, and what we measure, we have different. Then we have, for instance, polarization resistance, which is a very typical one for measuring instantaneous corrosion rate, polarization curves, extrapolation. We have voltammetry, that is very common for analytical techniques. Electrochemical noise, in which we do not apply any signal, we just listen to the electrochemical behavior of the system. We have also potentiostatic or galvanostatic techniques, in which we keep constant the potential or the current. We have some alternating current techniques. The most famous one is the electrochemical impedance spectroscopy. We don't have much time, so I will focus and will just mention a few examples of the application of these 2 ones, which are underlined here, the galvanostatic reduction and the electrochemical impedance spectroscopy. Starting with the first one, the galvanostatic reduction consists in the application of a constant current to our electrochemical cell. We then monitor the evolution of the potential over time, and we get a graph such as the one you see in the left, in which we have several steps which correspond to the different reduction processes that are taking place on the surface. For instance, in this case, this plateau you see at about minus 0.7 volts corresponds to the reduction of silver 1 to metallic silver. Then multiplying the current that we know by the time the process takes place, we can calculate the charge. And from the charge, and using the Faraday law, we can obtain the mass of the metal that has been reduced. And what is this useful for in our field? So, well, that allows us to measure the corrosion layers that have been formed or deposited on different metals. We have used that, for instance, and it is the example I am showing in the right, to measure the very thin corrosion layers that are formed on different metal samples that were exposed within a museum environment. This is an example of a work we did with the National Archaeological Museum in Madrid, in which we exposed lead, silver, and copper. Sorry, I'm just realizing that the labels are in Spanish. Plomo, lead, cobre, copper, and silver, plata. And you see in this graph that we have been able, in the case of lead, we use gravimetric measurements because the corrosion layers were thick. But in the case of copper and silver, the tarnishing layer were very, very thin, and it was not possible to measure them by gravimetric techniques. So we use this electrochemical reduction, the galvanostatic reduction, to measure the thickness of this layer. And by that, study was helpful for the conservation department of the museum to assess the corrosiveness of the different areas of different showcases of the museum. This is another example. This is something we have published a couple of years ago, in which we applied this quantification method of the galvanostatic reduction to assess the very thin tarnish layers that were formed on silver and copper during the OD test. In the OD test, probably most of you know this test, exposes these metal coupons to materials that might be found in a museum environment, with the idea of selecting those which do not produce corrosive emissions. The classical OD test is the evaluation of the classical OD test is done by visual inspection, but sometimes it's very difficult to distinguish between degrees of corrosion of the different samples. So by means of using this galvanostatic reduction, we can obtain these curves. You see again in the right correspond to the reduction curves of silver coupons exposed to different materials, different test materials. And we can, for instance, distinguish, you see with the red arrows, two different materials, MDF board and oak wood, that were visually rated with the same temporary rating. We can distinguish very clearly between them and see, for instance, that the oak produces like double the corrosion that is produced by MDF. So these are just two quick examples of galvanostatic reduction. Second technique that I will be explaining is the electrochemical impedance spectroscopy. This is one of the most popular techniques used for the evaluation of coatings since the 80s of the past century. So almost we are 40, 50 years that this technique is very well established in corrosion studies. It is not, let's say, a real spectroscopy, because we are not using electromagnetic radiation. But since we are doing a frequency swept in a wide range, we usually call a spectrum. The idea of this technique is that we apply, in this case, an alternating current signal, typically in the potential. You see the in blue the equation at different frequencies, and we register the response of the system in the intensity, which is a signal with the same frequency, but displays in the phase. So the relation between this applied signal and the signal we measure is the impedance that we obtain. And we plot this against frequency in a bow diagram, for instance, in the left, or also in the E-RIHS diagram in the right, in which we plot the complex in a complex plane display. We present the imaginary part of the impedance versus the real part of the impedance. This is, I have to say, this is a technique which is complex, mainly the interpretation of the results. It is not so difficult. This is, well, a disadvantage, I would say, of this technique, that the interpretation is tricky, but it gives a lot of information about the corrosion processes taking place. As I said, the interpretation is the trickiest part of that, and there are several approaches to do the interpretation of the results. A very basic one, which is very common in all fields and also in cultural heritage, is just to compare the modulus of the impedance. If you see in the right, it is plotted the modulus of the impedance versus the different frequencies. In the right side, you will see that all these samples start at the same, more or less at the same impedance. But when we move down to the left to lower frequencies, there are significant differences, like almost 2 orders of magnitude of the impedance at the lower frequencies. The impedance we have at the lower frequencies is the impedance of the whole system, the sum of the impedances of the different elements. And in this case, what we are measuring, the example I am presenting here, is the protective properties of different oils that were used in scientific technological objects. This is a work that was presented in the ICOM-CC Metal conference in Finland in September 22. So we compared different oils, and as you can see here, there are very significant differences in the protection, in the corrosion protection offered by these different oils. So this is a very simple approach that can be only by this we can obtain a very relevant information, especially for conservation purposes, that will help the conservators of the museum to decide whether some oils need to be changed for others, or which ones can be used for protection. This is another example, another work we did. This one was made within the Hyperion CH project. The previous one of Hyperion HS was done in collaboration with many other groups. In this case, we made this test on bronze coupons that were to which different coatings were applied and were artificially aged, and we tested the behavior of these coatings. And as you can see here in the top left, I am presenting in this histogram the modulus of the impedance of the different coating systems, Waxes, Paraloid, B42, and the combination of both. And you can see how we can compare the performance of the different coatings. You see, for instance, that this double layer, this double system, in all cases have like 2 orders of magnitude higher impedance than the wax alone. The wax alone hardly improves the corrosion resistance of the surface. And we can also compare in the light blue and dark blue the behavior of the coatings before and after the artificial age. If we want to go deeper and really want to get into trouble, we can use equivalent circuits for the interpretation of the results. Equivalent circuits are electrical circuits that are used to feed our data, and in which the different elements we put in the circuit represent the electrochemical response of different elements in our system. For instance, you see in the most simple one, in which we have Re, which is the resistance of the electrolyte, and then we have 2 elements in parallel, a capacitor and a resistance. In a bare metal, this capacitance is due to the double layer capacitance of the metal immersed into electrolyte. and the resistance stands for the charge transfer resistance. That is the resistance associated to the oxidation process of the metal. This is a very simple one. The circuit we can use, for instance, to model the behavior of a coating is similar to this one. You can see it in the top right in this scheme. We again have in the left the resistance of the electrolyte, and then we have again in parallel this capacitance and the resistance, but in this case they are due to the capacitance and the resistance of the coating and the organic coating itself. When this is, let's say, the most simple one, but this can become very complicated. For instance, we can, when we have some pores of this coating degrades, the electrolyte reaches the surface of the metal, and we have the circuit you see in the bottom right, in which we have a nested circuit in which we have the double layer capacitance and the charge transfer resistance nested in series with the resistance of the pores, and in parallel all them with the capacitance of the coating. To this, we can also add other elements related with diffusion impedance, or we can use other elements such as the constant phase element, which is represented in the bottom left. The CPE stands for, this is an empiric element which is used in this kind of fitting to model the distribution, the non-uniform distribution of currents or thickness of the coatings or different types of inhomogeneities in our system. So the interpretation of this using equivalent circuit is a very hard topic, and it would take us a lot. So I am not going much more into detail of this, just to let you know about this, what is this about. Now, I mentioned that we can use these techniques in situ, but you might be thinking, how can we take a whole statue into this electrochemical cell? Of course, we cannot. So what we have to do is to just do the opposite and to take the cell into the statue. This is something that it is not easy and has a lot of practical complications, mainly managing and handling a liquid electrolyte. And to tackle all these problems, we developed in our research group some years ago an electrochemical cell in which we replace the liquid electrolyte with a jellified electrolyte. This is what we call the gel polymer electrolyte cell, GPE cell. I am leaving here some references. If you are interested, you can see more details of that. To make it brief, I will just say you can see here the elements I already mentioned in the scheme in the left. You see that we have the counter electrode, the reference electrode. We made the electrical contact for the working electrode with the statue itself. And what we do is that we put this cell as a probe on the surface of the metal of the sculpture we want to measure. In the photograph in the right, you see this more, let's say, cloudy substance is the jellified electrolyte, which protrudes in the bottom, so we can put that on the surface. And you can see here some real examples of these measurements, field measurements. You can see in the left, we're measuring the bronze statue, and again in the National Archaeological Museum in Madrid. In the center, it is my colleague Blanca Ramirez. This is part of one of the MOLABs that we carried out under E-RIHS. And in the right, you can see a photograph of this very morning of myself measuring some sculptures of Jorge Oteiza in the city of Pamplona here. This has been taken this morning. And what can we learn from that? For instance, you can see here with the example of the bronze sphinxes, we measure them before and after a restoration treatment. And you can see in the left, these are the modulus of the impedance in two different parts of the patina, what we call the dark patina in the top and the green patina in the bottom. you can see that before, which are the solid dots, the impedance is lower, but when we know, the restores apply the treatment, the impedance increases by almost 4 orders of magnitude. We plot them, the modulus at the low frequency versus time, which is the graph on the right. You will see how increases, and then we follow that over time, measuring exactly on the same places, and you can see how we can follow the degradation of the coatings. The degradation, not in chemical terms, we are not analyzing the composition or the degradation, the chemical degradation, but what we are measuring is the actual performance, the degradation of the actual protection performance of the coating. Or here we did something similar. This is a real example of this project, this MOLA project we carried out in Arcantic, Nantes, in which they wanted to compare different coatings to be applied on for the protection and conservation of heritage artifacts. This is an European project, international project they are running, the ProCraft project, and they wanted us to test different coatings. And you can see in the right how while the data are a bit noisy, this is typical when we measure in the field. It is the spectra are not so nice and so smooth, but again, we can see that there are relevant differences between the different coatings. Of course, I cannot show you which ones are them. This is still something that hopefully will be published in the coming months. So hopefully you will be able to solve and to know what is under that question mark. So that's all from my side. I would like to thank you just with these photographs in which you see me again in yesterday morning. Sometimes measuring the field is not so easy and comfortable. It started to rain, so we have to cover all the instruments, all the instrumentations. Luckily, it was just a moment and we were able to finish with it. I finish with this. I leave you here my email. Of course, I am now happy to answer any question you have, or if you have in the future any question or comment or want to contact me, you will have here my email. And that's all from my side. Thank you very much.
Thank you very much, Dr. Cano. And I would like to introduce our next lecture that will be presented by Emilio Cane. And it will be on archaeology and on studies on human evolution. It will be on June 27 at 3 p.m. Rome time.